Alright, welcome back. Today we are going to talk about spectral decomposition. Spectral decomposition, also called eigenvalue decomposition, is an alternative method for obtaining the square root of a matrix. Spectral decomposition is a matrix factoring method that also has important uses in finding powers of square matrices and expressing relationships among square matrices. The more general matrix factoring method of singular value decomposition has the same uses for any rectangular matrix. So, decomposition is the process of finding the roots of a matrix or factoring it. It is the matrix analog of finding the roots of a polynomial such as this one here. A squared plus 2ab plus b squared, we can easily factor into a plus b times a plus b, which is just a plus b squared. As everyone who has tried it knows, it's much easier to find the square of a polynomial such as a plus b squared than to find the square root of a polynomial such as a squared plus 2ab plus b squared. Particularly if the polynomial is a more difficult one, such as 3a squared minus 5ab plus 4b squared. But there are algorithms to do so. So it's the same with matrix algebra. It's much easier to multiply matrices or a square matrix than to find the square roots of a matrix. But there are algorithms for such things. So the two major methods for finding the square root of a matrix are triangular decomposition and spectral decomposition. The two give very different kinds of root matrices. The square root matrix that is found with spectral decomposition, which we're going to talk about now, is symmetric. And as the name implies, a square root matrix that is found with the triangular decomposition is a triangular matrix. However, both qualify as being true square roots of the target matrix, in the sense that the root matrices created by either of the methods, when pre-multiplied by their transpose, will yield the original matrix. So like I mentioned, we're going to talk about spectral decomposition today, and we're only going to use Excel to do so. Spectral decomposition means finding the roots of a square matrix by the process of eigenvectors and eigenvalues. That's why you can also call it eigenvalue decomposition. The eigenvectors in this case are analogous to primary colors, from which all the colors of the rainbow can be constructed by mixing the primaries in additive combinations. In the same way, the entries of the original matrix can be constructed by combining the eigenvectors of the matrix in additive or linear combinations. Any power of a matrix can be obtained by the method of eigenvectors and eigenvalues. Eigenvectors are not only eigenvectors of matrix A, for example, but also eigenvectors for any power of matrix A, including the 1/2 power of matrix A, the square root of the matrix, and the -1 power of matrix A, the inverse of the matrix. Therefore, either the inverse or the square root of matrix A can be obtained by the process of obtaining the eigenvectors and eigenvalues of the matrix. So, obtaining the eigenvectors and eigenvalues of the matrix, like we did in the previous video, is very crucial. So let's consider the matrix A that was used for the previous video. We're going to have a 3x3 matrix with the values of 4, 6, 2, 6, 16, 3, 2, 3, 9. The fundamental equation for spectral decomposition is this one right here in cell L3. A equals C times D times the transpose of C. It shows that the matrix A can be reconstructed by the product of C, the normalized eigenvectors of A, which is what we called in the previous video as X, and we see the values here. And that's multiplied by D, the diagonal matrix of eigenvalues, which we called lambda in the previous video, which I have here. And that is multiplied by the transpose of C. So once again, this equation right here in cell L3 is the fundamental equation for spectral decomposition. And as I did mention, our matrix C here is the normalized eigenvectors of A, and we'll talk about normalization in a couple more videos from now. But essentially what that means, if matrix C is the matrix of normalized eigenvectors, means that they are normalized to 1. And the matrix of normalized eigenvectors for matrix A is found to be here, which we've had in the previous video, and once again called X. And what we call lambda is what we're going to call D for this video. So once one has obtained the normalized eigenvectors matrix C and the diagonalized matrix of eigenvalues D, they can be used to obtain any power of matrix A by a very simple process of matrix multiplication. This is because the eigenvectors C are not only eigenvectors of C, but also of any power of C. That's very important to know. Therefore, various powers of A can be obtained from these variations of this equation right here. So you can have A squared equals C times D squared times C transpose. And the inverse of A, you just change the D to the inverse of D. And A to the 1/2 power, you just change D to the 1/2 power. So once again, to obtain any power of A, we just enter the D matrix to that power in the midst of this equation. For example, let's do A squared. A squared can be obtained from this formula here. So we first need to find D squared. So what I'm going to do is just make this equal to D, and then I'm going to square that. And hit Control Shift Return. That's what we get. So before I go on, I'm just going to demonstrate this formula up here. We can just have that equal matrix multiplication, and we're going to do it twice. So I'm going to do it all in one thing here. We're going to multiply C times D, and then comma the transpose of C again here. Close the parenthesis. Close the parenthesis. So we have, if you look at this part here, we've got matrix multiplication. We're going to multiply C times D, and then we're going to take that and do matrix multiplication and do that times the transpose of C. Control Shift Return, and we get these values which should equal A. Now if we change the width of our columns, it's just a little bit of rounding error here, we see that this is equal to A. So let's do this one down here. It's going to be the same idea. Matrix multiplication, we're going to actually have to do it twice. So we're going to take C, comma, this time D squared, close your parenthesis, comma, and we're going to multiply it by the transpose of C again. So note how easily one obtains the square of the diagonal matrix of eigenvalues D squared. Since it's a diagonal matrix, the square of the matrix is obtained by merely squaring the diagonal element, which we did. The square of matrix A can be easily checked by directly calculating it, and we confirm that our obtained A squared matrix by the spectral decomposition method is correct. You simply just multiply A times A. And it should give us the same thing. And once again, if we change the column widths, we can see that they're the same. pretty much with rounding error, of course. Now let's do the same thing, but let's find the inverse of a to the negative 1 power. It's obtained from this formula here in cell L11. And note how easily one can obtain the inverse of the diagonal matrix of eigenvalues, the inverse of D. Since it's a diagonal matrix, the inverse of the matrix is obtained by merely taking the reciprocal of each diagonal element. So we can take this one, it can be equal to 1 over this first diagonal element. Oops. 1 over the first diagonal element. And that can be equal 1 over the second one. And that will be equal to 1 over the third diagonal element. And the rest are just zeros. And it's going to be the same thing that we did up here in both of these. So what I'm going to do actually is just copy this formula so I don't have to type it out again, and then apply it here. The only thing we have to do is change the D. We're going to take, instead of D squared or just regular D, we're going to take the inverse of D. So highlight that, Control Shift Return, and we get these values. This inverse can be checked by showing that when A is multiplied by it, the result is an identity matrix, which is the formula that we have right here that we actually talked about in video 3.30 when we talked about matrix inversion. So we're going to do matrix multiplication and take A and then what we just found, the inverse of A. And of course with rounding error it looks like the identity matrix. Now finally we can get down to what we actually came here for, spectral decomposition. The spectral square root of matrix A is calculated in a similar manner. You just take D to the 1/2 power, which is taking the square root of it. And also note how easily one can obtain the square root of the diagonal matrix of eigenvalues, D to the 1/2 power. Since it's a diagonal matrix, the square root of the matrix is obtained by merely taking the square root of each diagonal element. So let's do that as well. So we can make this one equal to the square root of the first diagonal element in D. This one can be equal to the square root of the second diagonal and the square root of the third diagonal. And of course the rest are zeros. Now let's do the same thing that we have been doing. I'm just going to paste the equation that we had in before, and all we need to do is change the D element to the square root of matrix D that we just got. Control Shift Return, and these are the values that we get for the square root of matrix A. The spectral square root that we just got can be checked by showing that when it's multiplied by itself, the resultant is the original A matrix. So I have that equation right here. So when we multiply the square root of matrix A times the square root of matrix A, we should get the matrix A. So let's try that out. So we're going to do matrix multiplication and do the square root of A times itself. And in fact, we do get A. So there you go, that's spectral decomposition. Once again, the values that we found for the square root of matrix A are right here. The first value being 1.6547. And the next video we'll talk about the triangular decomposition, and we'll compare that to spectral decomposition. Have a good day.